Okay, back again already. It's pretty chilly this morning. It's a December morning. Okay, so chapter 17. We're going to go over today. And this is Minkowski's four-dimensional space. Hey Google, who is Minkowski?
On the website thefullerhouse.fandom.com, they say, Minkowski is a character in Fuller House. He is portrayed by Trevor Larkham.
She's our culture's more into other stuff instead of science. Alexa, who is Minkowski?
Pierre Minkowski.
Alexa, who is Minkowski?
Hermann Minkowski was a German mathematician and professor at Königsberg, Zurich, and Göttingen. He created and developed the geometry of numbers and used geometrical methods to solve problems in number theory, mathematical physics, and the theory of relativity.
Yeah, so there's a lot more people involved than just Albert Einstein, and trying to figure this out. Just Albert Einstein's kind of gets like most of, most of the credit in a way. Maybe, I mean, a lot of other people that probably not even spoken about deserve credit for these ideas. Um, just like the first man to land on the moon, most people think, oh, that's Neil Armstrong, but it was actually two people that landed on the moon at the same time. That was Buzz Aldrin and Neil Armstrong together. And what were the first two words spoken on the moon? Most people think is it's one small step for. It missed the word A, but Amen. Uh, one giant leap for mankind. But it's actually the first two words spoken on the moon were contact light, which is the little cyan-colored light on the lunar module that lit up, which indicated the lunar module didn't crash on the moon. So those were the first two words spoken on the moon, and that was by Buzz Aldrin. So, anyways, just as a little side note for your enjoyment. Okay, so this chapter 17, Minkowski's four-dimensional space, is not too long. There's just one equation in here. Don't let the equation scare you. But here's the equation. All right, take a look at it. Scary equation. It's not written in Chinese. It looks like Einstein's got square root of -1 in here. That's where you use the imaginary. Yeah, imaginary numbers are fascinating. You We take a square root of a negative number, and what happens is we use in math, you use the I for imaginary. Some other people may use a different symbol, but I've gotten myself addicted to coffee. I used to not drink coffee for most of my life, and then I went to Costa Rica and I had a cup of coffee, and then I started drinking coffee. Tea is probably better for you. I'm just guessing. I'm not. I'm not a. I have no idea. Okay, so Minkowski's four-dimensional space. I'm gonna just go ahead and read, and we'll see what happens. So the non-mathematician is seized by mysterious light, no, shuddering when he hears of four-dimensional things, by a feeling not unlike that awakened by thoughts of the occult. Hey Google, define occult.
Here's the definition of cult: a system of religious veneration and devotion directed toward a particular figure or object.
Hey Google, define OCCULT.
Here's the definition of occult: supernatural, mystical, or magical beliefs, practices, or phenomena.
Magic. You know, most people on the planet believe in magic. They just don't want to admit it. And it's nothing wrong with believing in magic. Okay, so and yet there is no more commonplace statement than that the world in which we live is a four-dimensional space-time continuum. Space is a three-dimensional continuum. By this we mean that it is possible to describe the position of a point at rest by means of three numbers, coordinates x, y, z. So, x, y, and then z. They're all perpendicular, which right angles are 90 degrees to each other, or pi over 4. No, pi over 2. Um, and that there is an indefinite number of points in the neighborhood of this one, the position of which can be described by coordinates such as x1, y1, z1, which may be as near as we choose to the respective values of the coordinates x, y, z of the first point. In virtue of the later property, we speak of a continuum, and owing to the fact that there are three coordinates, we speak of it as being three-dimensional. Similarly, the role of the physical phenomena, which was briefly called world by Minkowski, is naturally four-dimensional in the space-time sense. For it is composed of individual events, each of which is described by four numbers, namely three space coordinates x, y, z, and a time coordinate, the time value t. Now, time, in order for time to go by, you have to have motion, because there's no clock in it that we know of, that anybody knows of, that doesn't measure some kind of motion. Even not just mechanical clocks, but electronic clocks, they got to measure the motion of the voltage, measure the motion of the change in current, the change in motion of electrons, essentially, or holes. Uh, there's what's called Hole flow theory instead of electron flow theory, where you have positive charges moving around. Uh, okay, so time coordinate value t. The world, quote unquote, world is in the sense also a continuum for to every event. There are as many neighboring, quote unquote, neighboring events realized or at least thinkable as we care to choose the coordinate system x1, y1, z1, t1, of which differ by a definitely small amount from those of the event x, y, z, t originally considered, that we have not been accustomed to regard the world in this sense as a four-dimensional continuum is due to the fact that in physics, before the advent of the theory of relativity, time played a different and more independent role as compared with the space coordinates. It is for this reason that we have been in the habit of treating time as an independent continuum. As a matter of fact, according to classical mechanics, time is absolute. To say it is independent of the position and the condition of motion of the system of coordinates. We see this expressed in the last equation of the Galilean transformation, t prime equals t. Hey Google, tell me about the Galilean transformation.
According to Wikipedia, in physics, a Galilean transformation is used to transform between the coordinates of two reference frames which differ only by constant relative motion within the constructs of Newtonian physics.
Okay.
These transformations, together with spatial rotations and translations in space and time, form the inhomogeneous Galilean group.
Okay. So the four-dimensional mode of consideration of the quote-unquote world is natural on the theory of relativity, since according to this theory, time is robbed of its independence. This is shown by the fourth equation of the Lorentz transformation. Okay, so I posted a previous video about how to derive the Lorentz transformation from a right triangle and Pythagorean theorem. So this is just kind of like maybe a little twist in that. I mean, you still can see that. See that equation? Don't let it scare you. Okay, so um, again, we have this divide by zero problem because the velocity of light, uh, velocity approaches the speed of light is 1 minus 1, which is 0, and any number pretty much divided by 0 is infinite. So and yeah, so if v approaches the speed of light on the top of the equation, the numerator uh, is t minus x. Okay, whatever. Anyways, moreover, according to this equation, the time difference delta t prime of two events with respect to k prime. K prime is the moving frame of reference. Delta t prime is the change in time in the moving frame of reference. So you got a clock and you're riding the train. Your change in your time as time goes by while you're sipping a cup of coffee in the train. That's what like delta t prime. Two events with respect to k prime. Okay, so k prime is the reference coordinate on the train. Does not in general vanish even with a time difference delta t. Now delta t is the guy on an embankment. Maybe he's drinking Corona instead of coffee, and well, he probably should be drinking coffee because you don't want him to run on the tracks. Anyways, delta t is on the embankment, so the time goes by on the embankment is the delta t. The same events with reference to k vanishes. Wait. Okay, so I'm just going to continue reading. Pure space distance of two events with respect to k, which is again a static embankment frame of reference, results in time distance of the same events with respect to k prime. Now k prime's on the train, so you're on the train, drinking beer or coffee or whatever. But the discovery of Minkowski, which was of importance for the formal development of the theory of relativity, does not lie here. It is to be found rather in the fact of his recognition that the four-dimensional space-time continuum. My computer is telling me to do something. I'm becoming a slave to my computer. Anyways, it is to be found rather in the fact of recognition of the four-dimensional space-time continuum of the theory of relativity in its most essential formal property shows a pronounced relationship in a three-dimensional continuum of Euclidean geometrical space. And there's a footnote here. It says, CF, the somewhat more detailed descriptions in Appendix 2. In order to give due promise to this relationship, however, we must replace the usual time coordinate t by an imaginary magnitude square root of minus 1. CT proportional to it. Hey Google, what does CT mean?
CT scan stands for computed tomography scan.
That's not what I'm asking for. Alexa, what does CT stand for?
I'd rather not answer that.
Alexa, is your nickname Hal?
Sorry, I'm not sure.
If you know what HAL 9000 is? Alexa, tell me about HAL 9000.
HAL 9000 is a fictional artificial intelligence character and the main antagonist in Arthur C. Clarke's Space Odyssey series. First appearing in the 1968 film 2001, A Space Odyssey, HAL is a sentient artificial general intelligence computer that controls the systems of the Discovery 1 spacecraft and interacts with the ship's astronaut crew.
Thank you, Alexa. Under these conditions, the natural laws satisfying the demands of the special theory of relativity assume mathematical forms in which the time coordinate plays exactly the same role as the three space coordinates. Formally, these four coordinates correspond exactly to the three space coordinates of Euclidean geometry. It must be clear even to the non-mathematician that, as a consequence of this purely formal addition of our knowledge, the theory perforce gained clearness in no mean measure. Their inadequate remarks can give the reader only a vague notion of the important idea contributed by Minkowski, without the general theory of relativity, of which the fundamental ideas are developed in the following pages, would perhaps have got no farther than its long close. Minkowski's work is doubtless difficult of access to anyone inexperienced in mathematics, but since it is not necessary to have a very exact grasp of this work in order to understand the fundamental ideas of either the special or the general theory of relativity, I shall at present leave it here and shall revert to it only towards the end of part 2 of this book. Okay. And that's the end of this chapter. Okay, so time is robbed of its independence. I mean, basically, this chapter seems to be centered around this equation, and I'm not exactly sure how that equation is derived, other than the Pythagorean theorem aspect. But the numerator is kind of interesting. Um, so yeah, this chapter is. I mean, if you want to learn more about it, go research Minkowski's four-dimensional space. Hey Google, tell me about Minkowski's four-dimensional space.
Sorry, I don't have any information about that.
I'm probably not pronouncing it right. Alexa, tell me about Minkowski's four-dimensional space.
From fandom.com. Four-dimensional space is a space in which each point requires a quadruplet of numbers to describe its position.
So I really don't know what to make of this chapter, other than I mean, we're using a time variable, and what happens if you're moving in a train and your time slows down relative to the guy drinking a Corona or something on the shore. I hope you have coffee on the embankment of the train track, and so the observer on the ground looks at your clock, and your clock's going by slower than his clock uh, or her clock, whoever's on the embankment, while the clock in the train is going. I mean, if you're sitting on the train, you look at your clock's going normal speed, but if you look at the clock of the guy sitting on the embankment drinking hopefully coffee, I'm out of coffee, but anyways, drinking that, and you'll see there. So on the train, you see the clock of the person on the ground. And that clock is going faster for some, but this is at really high speeds. Okay, so not like our what we see in everyday life speeds, but this is like super fast train. Like I don't want to say Japanese train. Japan's got one of the faster trains. Hey Google, who's got the fastest train in the world?
Here you go.
Alexa, who has the fastest train in the world?
The Shanghai Maglev train.
So China's got the fastest train in the world. Hey Google, who has the fastest train in the world?
China. On the website CNN.com, they say 1. Shanghai Maglev 460 kilometers per hour, 286 miles per hour. China. The world's fastest public train is also unique. It's the only link in the world currently carrying passengers using magnetic levitation rather than conventional steel wheels on steel rails.
Okay, so China's kicked the United States' butt on trains, and Japan has too. In the United States, we just have these slow. I mean, I love Amtrak. I don't want to put Amtrak down at all. I love Amtrak, even though they're slow trains. But I have to admit that I am envious of China and Japan's high speed trains. I think it's really neat that I understand that Elon Musk is working on the. I'm trying to remember the name of the train. Hey Google, what's the name of the train that Elon Musk is working on?
On the website
It's Hyperloop.
fastcompany.com, they say, maybe Elon Musk should have skipped the Hyperloop and built parking lots instead. Do
Hyperloop.
you want a little more context?
Hyperloop. That's okay.
Indeed.
Alexa, tell me about the Hyperloop.
A Hyperloop is a proposed high-speed transportation system for both public and goods transport. The idea was picked up by Elon Musk to describe a modern project based on the VAC-train concept. Hyperloop systems comprise three essential elements: tubes, pods, and terminals. The tube is a large, sealed and low-pressure system.
Okay, so anyways, to get a faster train than everybody, we can fly even faster than commercial aircraft if you have a vacuum. Because see, the problem with commercial aircraft is air is going to be resistance from the air is going to push against the airplane. But if you have a vacuum tube, you can have a train go faster than commercial aircraft inside a vacuum. and that's what this hyperloop idea is. If you ask me, I really think we should have vacuum tube connections between every major city in the planet so that everybody can get everywhere really fast. But we don't have that because we prefer to uh, act like chimpanzees. That's a whole other topic. I don't want to go into political stuff, but maybe we can learn something from primates. Uh, but yeah, what do you say? Kudos or congratulations to China for having the fastest high-speed train in Shanghai. I'd like to visit that someday. Um, I really wish the United States would have faster trains, but who knows? Maybe someday we'll figure it out, or maybe we won't. Who knows? But that's the end of this chapter, and the next chapter is part two. It's called the General Theory of Relativity, and chapters 18, Special and General Principle of Relativity. And that chapter is 4 pages, not too long, not too bad. I give credit. Maybe that's why Einstein. So this is where we're at. Okay, not halfway, but we're starting to get there. Um, that's one way. How Einstein, the fact he's got short little sections or I think he calls them sections, not chapters. I'm calling them chapters, but if you break problems down to the smaller pieces, that's how you solve problems. And anyways, that's a good way to solve problems and explaining because it's hard to explain. I feel like it's never really been. I've never really understood this, but I'm starting to understand it a little more. I mean, I like the idea that okay, you can use the Pythagorean theorem to derive from a right triangle. You can derive the Lorentz transformation. I didn't know that till just the last few days. So hopefully you learn that too. And you take care of yourself and have a good day. I've got work to do, and you or play. I try to make work as play. That way it doesn't feel like you're working. Anyways, yeah, take care of yourself. Have a good night, good evening, good morning. I'll shut this light off and take care.